Hi, Vsauce. Garrison here. Oh, this is a car. Speaking of cars, moving objects. Speaking of moving objects, special relativity exists. But what is special relativity? Confusing. I know. But in a practical sense, special relativity is just an improvement on Newtonian physics. See, Newtonian physics does a great job when it's explaining the velocity of really slow-moving objects, like this croquet ball. But if you want to explain how things behave when they move really fast, like 50% or 80% the speed of light, for example, me on this scooter, then you need special relativity. You see, objects behave differently when they travel at really high velocities. For instance, the faster something travels, the more massive it becomes. And the faster something travels, the shorter it will become in the direction that it's traveling. It'll also travel through time at a slower rate relative to everything else. But each and every one of these main principles, main effects of traveling at extremely high velocities is just an extrapolation from the two main principles of special relativity. First principle is that the laws of physics are upheld in all frames of reference. Second principle is that the speed of light is the same in all frames of reference in which nothing's accelerating, no matter how fast the objects in the frame of reference are going themselves. These two principles have drastic implications for the laws of physics. To better explain how these phenomena interrelate, we can use the example of the near light speed train. But how much will the length of this train that's traveling at 80% the speed of light contract? In order to determine that, we need an equation. In order to determine the length of an object while it's moving, you need to multiply its at-rest length by gamma in this equation. Thus, the length of the train while it's moving is equal to gamma times its at-rest length. But what is the result in this case? Well, we know the train is going at 80% the speed of light, so we can substitute in for v 0.8 c. And needless to say, once you solve this equation, you'll find the answer for gamma is 0.6. So the new length of the train, once it's traveling at 80% the speed of light, is 0.6 times 1,000 feet, or 600 feet. Let's say you want to rob a 1,000-foot-long train by trapping it in a tunnel. Now, first thing I might ask is, hey Garrison, you want to help? Absolutely. Second question I'm going to ask is, how long is the tunnel? In this case, the tunnel is 600 feet long, which makes the job seem impossible. I mean, how are you supposed to trap a 1,000-foot-long train in a 600-foot-long tunnel? It can be done. You see, according to special relativity, faster something travels, the shorter it becomes in the direction of travel. So, if the train is traveling fast enough to the speed of light, its length will contract to under 600 feet, and then we can trap it in the tunnel.
600 feet? Oh, but that's the same length as the tunnel.
Thank you, incredibly handsome student. So you see, all we have to do to trap the train is just close off either end of the tunnel as soon as the front of the train reaches the end of the tunnel. So that's what we're going to do to trap the 600-foot-long train in the 600-foot-long tunnel, even though the train is only 600 feet because of how fast it's traveling. simple enough to me, the train's in the tunnel, we close off either end and the train is trapped. But the people on the train will experience something completely different. You see, the people at the front of the train will experience us closing off the tunnel, just like we saw them experience. But at that point, the information that the train is stopped will travel from the front of the train towards the back of the train, while the back of the train essentially has no idea the train is stopped, and the train itself, the back of the train, will be racing towards the front. And the information that the train is stopped will meet the rear end of the train 600 feet down the tunnel, therefore trapping the train. And, so to us, observing the train, we see both ends of the tunnel being closed off simultaneously. But to the people on the train, the front end of the tunnel is closed off first, and then once the back end of the train is inside the tunnel, the back end of the tunnel is also closed off. To us, the closings of the tunnel were simultaneous, not for the people on the train. And these two accounts of events differ completely, but in their own frames of reference, they're both completely correct and valid. Measurements made by different observers can completely contradict, but they can both be right. You see, in relativity, it's all about perspective. That's the main takeaway of special relativity. What actually happens depends on how you observe it. It's not just that how the universe appears to be changes based on the state of the observer. The universe itself actually changes based on the state of the observer. We can change the world around us by changing our frame of reference. But that's just a theory. A physics theory.